Hello. So after this talks about infra, let's talk a bit about actual software and even more so about the preparation before we actually write software to get better reliability with some technique which is not well known, which is formal modeling. First, who am I? Where I'm speaking from about this? I'm a consultant, independent, and I work at a small company called Ozinet, mostly focusing on scaling up backend for applications on either a typical microservices stack with Go, Kafka, AWS, or whatever, or the legacy LAMP stack with MongoDB, mostly working on payments or publishing for media, government, and so on. So about TLA+, we'll see what that is, why you would want to use it, and what have some relevant success stories, and what's the value proposition. Is it useful to use it? Is it cost effective to use it? So the first thing is that TLA+ is not a programming language. So that's a strange beast indeed. It's a formal language to write specifications. And that's really not something you can translate to an actual code that can be executed. It was created by Leslie Lamport. You may know the guy because he created LaTeX, the publishing package on top of Tech. And it shows actually TLA+ started as an extension of LaTeX. So originally it was just a language to write mathematical proofs about temporal logic. We'll see what that is. And only later did it come to be a mechanism to build proofs on top of these mathematical descriptions. And the reason why it's different from a programming language is that it focuses on the behavior and not the implementation. That means if you have to write error checks or quantize operations or do various things which you do in actual code, there's no room for them in that kind of logic. You focus on sets. And the reason why you focus on sets is that it's based on something which is called the Zermelo-Fraenkel set theory with the axiom of choice. I've added details on the slides, which we can see later. Lamport is famous for being a Turing Award recipient and also for LaTeX. And that's how he describes himself in the course about TLA+. So why would you want to use something like that? That's to find design flaws, because the best code you can write won't do you much good if the spec to which it was written isn't completely correct. And so that means it's mostly useful if you have some complex logic to do, maybe some concurrent code which involved multiple microservices operating together, or even if you write in Go or other languages with internal concurrence, you have many Go routines working against each other, you are writing a protocol adapter or whatever. This is the typical use case for TLA+. And that allows you to come before traditional testing. Because when you write tests, you typically write what you have been able to discover as possible issues in your code. But even if you do first tests to extend the scope of your testing to increase reliability, you're still limited by what the system has been able to generate. However, if you work from the design itself, before the code, you can describe the properties which your code is supposed to carry, like invariance, for example, or the fact that some states are reachable and some are. And you can put this as constraint, write the model describing that, and then launch a simulation to see if it actually verifies these properties. And that works because the most expensive bugs are the design flaws. As I said, if you have a bad design, the best code you write to it cannot be completely operational. What are some notable use cases for TLA+? The most publicized one is probably Amazon S3. You all know S3, I guess. That's a very large-scale storage system. And they described how it enabled them to find bugs in their design, in their protocols, and actually change how they would actually implement that. A few years later, Microsoft came to the same conclusion and used it to model Cosmos DB, which is a clone, for want of a better word, of MongoDB. And they wanted to ensure that the replication across the instances of the servers was consistent. Again, we see concurrent applications and the need to prove consistency and verify some properties about the code. There's also a large series of use cases in Kafka. Someone mentioned Kafka earlier, and some protocols in Kafka are complex. Kafka, that's a bus for large-scale messaging, to simplify things a lot. and it builds on replication. And like MongoDB or Cosmos DB or S3, replication is something which is inherently hard to get right. And so it started with the first time they tried to implement replication without Zookeeper for the K-Raft protocol, that's KEEP 966. And then after it would prove to be a success, it was extended to other extensions to Kafka itself to increase the reliability of that over time. If you look at these papers, every time they said it saved months of debugging, and in some cases, like Amazon and Azure, it would prevent outages for these services, which translates to direct financial impact. So that sums up the value proposition for these techniques. It's basically, if you fix something in the design phase, it may cost 1 unit of whatever. But that will be 1/10 of what it would cost if you find it during development, and maybe 1/100th or even more of what it can cost if you find it at runtime and your product has launched and is intrinsically flawed. You can avoid that by fixing upfront at the design stage. TLA Plus helps you find bugs which you wouldn't find with tests. And since it's complex to use, it's especially valuable when you are building complex things like distributed systems. If you have a simple website that just takes data from a database, formats them, and puts them to the page, there's no point in using TLA Plus. That's just not complex enough to be worthwhile. So how does it work? TLA Plus fundamentally is built on a technical or theoretical logic foundation. You've all done logic when you were students or even in high school, and you know that usually for whatever P is equal to P. That's some foundation of logic. However, that does not take the temporal element into account. Is P always true? Is it true that P at one time is the same as P at another time? And you don't usually describe that with logic. And that's the whole point of saying, for example, if P is the process is running now, that's a proposition. It can be ascertained as being true or false, but that does not mean that value will not change over time. Any process at some point will not have started and will eventually end. So that means that whatever P is not always equal to P at another point in time. And that's the limitation of traditional logic like we learn in high school or maybe later. Temporal logic adds that time dimension when you change the value of now. There are actually multiple branches of temporal logic. There's the linear one, which is the simplest of all, which was introduced in the late 70s, and that's what TLA Plus uses. There are actually more complex logics about time. We don't need to use them, although there are tools to model these other kinds of logic about time, but we don't need to care about those. Let's take a simple example. A light switch, click, it's on, it's off, and you can model that as a finite state automaton. If the light is off, I can click my switch and it will be on and back. That's quite simple. We have two actions, turn on, turn off, two states of on. We wouldn't want to write a model for that, but we could. And that model says, initially the system starts with light off. That means this is our init state. And we can describe an action by saying it is true that light is off and light prime, which means light after the next transition, will be on. And this is how you express a property about a change in time. Initial state, this is light here, and final state, light prime, this is a primed variable, means after the next iteration on the state machine, you get the property. And then it's always true that turn on means that light was off and it was on. And indeed, we have a single arrow here matching that. Same for turn off. And what describes the fact of going from one state to the next is that it's either one of the actions or the other. Then that reverses the point of view, turns it on its head. We started with the states, and here next is about the actions, the transitions. We could also have a push toggle. I push it on, I push it off, and it's pretty much the same model, but there's only one action. It's simple, and the formula in TLA Plus is even simpler. So what are actions? If we go back with what I just described, actions are the way we describe the system's step from one state to another. That since this is about transition, it enables you to get preconditions, things which must be true before the state transition, and post-conditions, things which must be true after the transition. In our last example, after the toggle action, we have either on or off. And the way we represent that in TLA Plus is by adding a prime after the name of a variable. If we go one step up in complexity, let's consider traffic lights, where you all know traffic lights. They're usually green, yellow, red, green, yellow, red, and so on. And that always goes that way. You can go, you can must to stop, and you have to be stopped. And you restart from the top. This means a simple loop like this one. You see, we have initial state, same as previously. Our transitions are now more complex because we can go from red to green, from green to yellow, yellow to red. And the way we describe our system is what is called a spec. That means we are either in the initial state or any number of iterations of the next transition, which is here, applied to the light variable. This is a description of a simple automaton like that. However, if you've been to Spain, you may have noticed that they don't work exactly the same. In Spain, you start with green, you go to yellow, then red. Then you go back for a short moment to yellow from the red before returning to green. So you could model this like the previous one by just adding one transition. However, there's a problem. If you think about it, just because you expect to go along that route, that doesn't mean that this would be forbidden. And actually, the automaton allows it, meaning you have to add one parameter in that case. And then your automaton changes like this, because you added two conditions, two variables to describe your state. And that's the process which you have to go through while you are discovering your algorithm. You try to describe your states and what transitions are allowed, and this will enable you to discover the additional variables which you may not initially be aware of. Because you will see that some transitions will be possible if you don't add them, and then you will know that you had to add them, and that will maybe simplify or sometimes complexify your design, but it will enable you to make sure what your invariants are. And that gives us a number of properties about an algorithm. We have two classes of them. The first one is safety properties. We want to describe what should never happen. For example, we should never be stuck in a loop. We could not have the light have both red and green lighted at the same time. This is a safety property, and this is described by your automaton and your TLA Plus spec. But you have another kind of property which is less intuitive, which is the liveness property. Whereas the safety property describes what happened at a given point in time, a liveness property describes what must happen over the course of time. And you have multiple ones of those. For example, you want to ensure that something will eventually happen. Consider, for example, our traffic lights. Just because you have this cycling behavior doesn't mean you can stay in one place if there's nothing happening. You want state transitions to happen, and that's being alive for the automaton. And you can also describe that with properties about the iterations and the fact that the transitions actually happen. Now, I said initially TLA Plus was about writing, describing behavior and writing mathematical proofs. Originally, it was just for layout. It was an extension of LaTeX. And at some point, someone who was not Lamport had the idea to try, since it's so formal, could we actually simulate running these machines? And they created the first model checker, and that's TLC. TLC actually takes all the descriptions that can be extracted from the language, builds all the arcs, all the transitions, and runs everything. Later on, another model checker came to be, which is called Appalachian, not sure how it's pronounced. And that one builds on the symbol of the representation itself. It does not just do brute force work like TLC does. It tries to do analysis and symbolic logic. That's much more complex, and it doesn't just work like TLC does. So for most purposes, you will start by TLC if you really want to do that kind of work. The process is you define the system, like we did for the traffic lights, and you try to find what should not vary. These are called invariants. You try to find all the temporal properties like liveness, safety, whatever, and the system will find for you the cases when you go out of these invariants, they stop to be invariant, or the cases where the system deadlocks. And the model will verify these properties at all iterations on all state transitions. I'm not going into detail, but here you have a complete example for the Spanish traffic lights. we have the TLA model we wrote a moment ago. The safety properties here saying light must always be one of these three colors we defined here. We have the fact that going to green is a Boolean, saying we may not return from indefinitely from going to red, yellow, and so on. And we can here have a temporal property saying at some point, if we are in yellow, we are going to go to green or red. So here you describe a property of behavior over time. Then you configure the modular saying, let's start in the init state. What describes the step we're taking is the next property, the one we have in here. That's the most of the logic we write is actually here. Then we say this is an invariant, this is a property, you can put however many you want about this, and they will all be checked every time. And you may allow or disallow the check for deadlocks. And finally, when you run that command on the CLI, you see it run, it generates states, it tries to prune the state space to optimize, and warns you if it finds a devlock or an invariant that tries to vary. How does it look in practice? You saw that probably here. This does not look like code. Some symbols do not look like something you can type, and that's because it's LaTeX originally. So you write it in a source form, just like you would write LaTeX, and you compile it with the TLA plus compiler, and that generates a PDF or another kind of rendering, which has all these symbols. Basically, what you have in your code is states. This describes all the properties which you want to name, basically, or the name of the states, like the light is green, the light is red, and so on. The variables store the state of that system, and they are the one which can take the values. And there are a limited number of types of values available. In most cases, you will be using sets, but you also have sequences and simple integers. You don't have floats, you don't have complex, you don't have vectors, you don't have many things. It's basically based on sets, and by extension, single values like integers. A few operators, you define a property like this. Implication is in the mathematical sense. It carries no philosophical behavior saying that this implies this. It only says that if this implies that, if that is false, then this was false. That's all. You have the and, the or, equality, and membership. And that's most of the symbols that make up the language, really. And then you have prime variables. As I said, they describe the same variable before and after a transition. And when you say light of prime is green, that means the state of the light variable after the transition will be green, whatever it was before. And when you write light is red, that means this is a precondition. If we want to try and take a step, it will only apply if this condition is verified. And this is the post condition, meaning where we go after the step. TLA Plus allows you to describe also stuttering steps, which is what happens when the system doesn't change. For example, consider traffic lights again. You don't want to have traffic lights moving in a circle at the maximum speed of time, which is the quantum of time from whatever constant that is much too slow. You want to stutter for an incredible amount of time, like several seconds or tens of seconds before taking transition. So most models will always allow transitioning from one state to itself on any number of time before going to another state. That's stuttering, and it's absolutely essential. And transitions are this. A prime variable is the same as the non-prime variable. That means we have taken a step from one state to itself. Temporal formulas describe what is going on. So something will always be true, something will be true at some point, and if there's something happens, then another thing will happen at some point. The specifications are the document you write about all the invariants and all the properties. And here is a simple example. You see, that's a mutex. That's something which you probably wrote more than traffic lights. And with just two processes, here's what that generates you can generate the state chart with TLA+. And if you go to three processes, this describes all the states of a mutex with three processes only. You see, there's a combinatorial explosion here, and the costs explode. You see, here we are in log size, and just with the number of processes, if we are at 12 processes, we are already at 10 million states. You can't try that to build that on your own and understand that in your head. So that's why you have modeler doing that for you. And that takes serious costs. Here's an example where I run the model. Can you guess when I started to run the model checker? normal use of the machine, model checker. All processes, all cores on the machine are completely full. This is not something you want to run in a cluster on a shared environment like was described earlier today. Here's the complete example for the mutex. We have no time to go over it, but it's in the slides. You can read it if you want. And to check it, what we do, again, we have parameters. Not everything has to be hard-coded. We can change the parameters to a simulation, and you just run the simulation with a simple command line like this. Because that language sounds very alien to programmers, there is actually another language which is called Pascal, which looks like a programming language, or actually two different programming languages that's called Pascal. Pascal looks a bit like Pascal if you use one of its syntaxes, and a bit like C if you use the other syntax it supports. And that's one strange thing of that code. The same program can be written that way, that's Pascal style, or C style. And if you try to use GenAI, like Gemini or Claude Sonnet or whatever about that, you will find that it doesn't understand the fact that one language has two different syntaxes, and if you ask for one, you will get the other, and vice versa. Because the agents don't understand the notion of one language having multiple syntaxes. Variables that can be assigned values, whatever. And the fact that you assign a variable value is actually meaning that you are taking a transition. And that's the whole meaning of transition. When you change a value in a variable which is not immutable in any programming language, you are effectively transitioning over time. And that's the link between your actual code and a TLA model. Pascal allows you to have atomic steps, multiprocess, and then it's translated to TLA+. In practice, when do you want to use that? As I said, when you write complex code, critical systems, and you want to do that very early in your design. For example, I recently finished the redesign of Kafka Consumer for Deliveroo, spent 6 months on it, and of the 6 months, I spent 2 months designing in TLA+ before starting to actually code. Another use case would be maintenance. When you have something which has been in production for long and is complex, has bugs, before you do a change to something sensitive, in addition to the tests, you might want to do some modeling. That can come at multiple points in your workflow. We have no time to go over that because I'm already over time. And you have many tools provided with the foundation, model checker, the plus compiler, formatter to PDF, and also a formal proof system. We have no time. And you have some tools with a UI like a profiler. You saw that it's up a lot of CPU. You may want to check where you are spending your time, and that's available in the toolbox. Finally, how do you use that in production? You start with a small program part, isolated, the more complex part of your system, and then you grow. Don't start with big, you will fail. There were previous experiments that delivered with that, and they failed. And this is the first time we actually went ahead with a project using it, because it started with a small part of the overall design. And then try to spread the knowledge, because not many people are ready to use that. Finally, a small secret that was described in a course about TLA+. Really, the only way you can write that at scale is to use state machines, and you need to have developers who understand state machines. Otherwise, it won't go through. And that's it. There are 2 books about TLA+, the original by Lamport, and a practical one, which is the one I would recommend. Or you can also talk to me if you're interested. Are there any questions?
One person. What's your pay? One person. You want to say you don't use that. Always wrong in assumptions or components when either or you right. Yes, the writing keyboard you writing components always sorry you read that only.
Okay, excuse me, I'm not sure I understand your question because I'm not a native English speaker. I think you mean basically how do you maintain code and use dependencies which you don't control, basically. Yeah, the reason is you don't, basically. This is something you want to use with code you write from scratch and which you entirely control. And that does not solve the issue about maintenance, because what can happen, and it's documented in a number of the use story case you can find, people write a model, then write the code, then the code is maintained and deviates from the model. There are a number of research papers, and all I've found at this point is still research to try to build synchronization points in the code, maybe in the form of comments which can be passed to generate new specifications which can be run in CI to see that the code still matches the model. But there are limitations. For example, in this project we just finished, I wrote the whole spec. I had to do it alone, and no one on the team would spend the time to learn TLA and the logic. And then I coded the product, and when we put out the first alpha, we found a bug. And we found a bug with observability because we had watched it in the profiler on Datadog, and something wasn't wrong. And guess what? The part which failed was in this critical component, which had been modeled with TLA+, but it was the part which was outside the model. It was the exit condition after the done state. Okay, when we are done, we need to exit the model still. And I had forgotten that, and it was an outside of a model case. You also need to take into account the fact what happens before you enter the model and when you leave the model. So no, there's currently no solution to keep code in sync with the spec. There are a number of attempts to still write generated code from TLA+. That won't be your operational logic, but you can plug into this generated code so that you call, or you are called from these fixed entry points, and that gives you some kind of harness to be sure that whatever you are doing between these steps, the logic between these steps remain in sync with the model. That's the best we have at this point.
Right.